11 o'clock on the first Sunday of the month. Good morning and welcome from Prithvi Theatre for yet another version of Chai and Why. For those who are attending online, do remember that the only way we can interact with you is via the chat. So please put your questions and comments in the chat. Those who are here, of course, you can raise your hand and ask us questions. If the audience asks a question, please just repeat it for the sake of the online audience. The online audience, of course, you'll have to make your own chai. All of you will get chai after the break, of course. It's a pleasure today to welcome Dr. Mohammed Ramiz from TIFR, who works in the area of, I guess it's called astroparticle physics.
Yes.
And he's going to tell us about a very, very exciting experiment called IceCube. And I'll let him talk to you about all that. So Ramiz started off his career in Kozhikode, from where he went to BITS Pilani, Goa, became a dual degree engineer and physicist, went to Geneva, the University of Geneva, did his PhD there, working also with CERN. After he finished his PhD, he went to the Niels Bohr Institute in Copenhagen, one of the places very important in the birth of quantum mechanics. He was there for almost 4 years, after which we were very lucky to grab him and get him to TIFR. And today he's going to tell us about this wonderful experiment called IceCube. I don't know if you've heard about it, but it's somewhere far away, right?
Yeah, it's at the South Pole.
It's at the South Pole.
One of the least accessible places on the planet.
Okay. So to hear more about that, over to you, Ramiz.
Yeah.
Okay. So remember, if it's a simple question, you want an immediate thing, you want to interrupt him, please raise your hand and ask. Otherwise, just wait. Once he's done, he'll take a lot of questions. After the chai break, we're not going to be online, so then you can ask him all you want. Okay. So that's it. And online audience, please remember to put your questions and comments in the chat. Over to you.
Thanks, Arnab, for this kind introduction and the opportunity. It's actually very flattering. Just 1 year back, I was...
Go to the slide share before we forget.
Yes.
Yeah, for the online audience, we'll share the slides. Just give us a sec. And there's no sound, right? Optimize for video clip. We'll play a video.
Yeah. Do I? Yes.
Do you have it on?
Yeah, I think there's a slight delay, but it's okay. I'm seeing the slide on YouTube.
You're seeing the slide? Yeah, I think this is fine now. Is it there on? It's there on YouTube as well, so you're all good to go.
Hey, thank you for this opportunity. I'm very flattered. Just 1 year back, I was sitting in there watching a play happening on the stage, and now I feel a bit like a celebrity. So I'm here to tell you about a new kind of astronomy that my collaborators and I have, in some sense, begun over the last decade, and that is astronomy using neutrinos. So, before we get to it, we need to understand what neutrinos are. And in our today's understanding of fundamental physics, everything that we can see, touch, taste is made up of the same things. There are 17 fundamental particles. Almost everyone in this room, I'm sure, has heard of an electron. You've probably heard of a photon also. It's just light in particles when you think of it. In 2012 or so, you would have heard of people discovering something called the Higgs boson, the God particle, which gives all particles mass. But at the bottom of this panel of particles, there are three that you see here called three types of electrons. There is three types of neutrinos, one corresponding to each lepton. A lepton is basically an electron and then its heavier cousins. And for these quarks, for example, they together make up protons and neutrons, which make up the nuclei. And they have interactions which are carried by these other particles. The success of this is that we can explain almost all physical phenomena that we see anywhere in the world in terms of this model and the interactions between them. So anything happening within this room, it's not surprising for a particle physicist. There are things out there in the universe, like dark matter maybe, that is not explained by this model, but this is the current understanding. So most of astronomy for the last 400 years or so that we have been operating telescopes has been done with photons. But in the last 10 years, we have started doing astronomy using other tools, and that's what I'm going to. So my slide changer doesn't seem to be working. Okay, now it's, nope, it's not. Let me Oh, there is just a big delay, I believe. Is that? Okay, so I'm going to place the context of this new astronomy that we have started within the context of broader all types of astronomy that human beings have been. Until about 400 years ago, we had no choice but to look at the universe with our naked eyes. There was no other instrument available to them. And then people like Hans Lippershey invented the first telescopes, which Galileo used to observe the universe with. And that itself was a pivotal moment in human history. The historians of science call it the Copernican revolution, the sequence of events that followed. There was events that maybe you have heard of involving Galileo and the church and the set of changes in beliefs among human beings that we are not at the center of the universe. But in the last 100 years or so, we have been able to, or maybe last 60 or 70 years, we have been able to build instruments that look at light, which is not visible to our eyes, but it's the same. It's just light at lower or higher energies. At higher energies, you have shorter wavelengths, so you get things like X-rays, with which you're able to also image your bones, etc. But you can take those same kind of instruments, put them in outer space, and you can see the universe in X-rays. You cannot do that from ground because the atmosphere is opaque to X-rays. So you really have to go outside the Earth's atmosphere. And at even higher energies, you have gamma rays, the highest energy photons we have ever observed. But at energies lower than that we can see with our eye, there is microwave and radio. And because we have started being able to image the universe in radios over the last 60 years or so, we now have large facilities like the giant meter wave radio telescope in Khodad near Pune, about which some of you may have heard in these sessions. And for example, in the 1960s, people started seeing that there is microwave radiation permeating all of the universe, and they started doing measurements of it. And they immediately realized the universe had a beginning, and the Big Bang idea came out to be. So, and around the same time, people have also started realizing that there are charged particles like protons coming in from outer space, and those are called cosmic rays. They usually interact with the atmosphere, and then they produce a shower of particles, and you have to detect them. And you cannot do astronomy with this because they're charged particles, they get bent by cosmic magnetic fields, you cannot point them back. Light travels in a straight line, which is why we are able to form images and see using it. In the last 10 years, so in fact, in the period between when I started my PhD and now, we have started two entirely new types of astronomy. One is using gravitational waves, which was for the first time announced in 2015 by the LIGO-Virgo collaboration. And the other was using neutrinos, which I was significantly involved in bringing about. So doing astronomy with neutrinos is what I'm going to tell you about. And the changing of slides is not. So the instrument with which we use to do astronomy with neutrinos is called IceCube, and it is a cubic kilometer of ice at the South Pole. At the heart of this instrument is this device called a photomultiplier tube. I actually have one right here of a different make. If anyone wants to take a look, please don't drop it. It costs about 40,000 rupees, but I can send it around. The advantage of this instrument is that it can count at the level of a few photons. So if you have like an extremely dark chamber or a room, you put a high voltage across its cathode and anode, and you look at the current that comes across it. If a single photon goes in, you see a pulse. Okay. Now, the other advantage is that this has a timing resolution. So it can tell you at what time the photon came with an accuracy of 1 part in a billion of a second or so. Around a few nanoseconds, 2 or 3 nanoseconds. So that is a highly precise instrument, which has been the mainstay of photon detection in high energy physics for the last 50 years or so. And IceCube consists of basically photomultiplier tubes. Now, these photomultiplier tubes have been put inside glass pressure vessels. So this is a spherical glass vessel, which can withstand a pressure of up to 650 bar, which is the pressure at the bottom of the Antarctic ice. And along with the photomultiplier tube, you will see a board, which is basically like the motherboard of a computer. It has a bunch of electronics sticking out of it, and those electronics allow you to shape the signal that comes out of the PMT and digitize it, turn it into ones and zeros, so you can analyze it on any regular computer, which is what we do. And many of these pressure vessels have been placed along strings, and then you drill a hole in the ice using a hot water jet, and you lower the cable into the ice, and then you pour the water back in, you let it freeze. And that is how IceCube was built. So my slide changing is just not working. I'm going to. So this is a schematic view of the IceCube Neutrino Observatory as it is today. It is at the South Pole, at the geographic South Pole, near the Amundsen-Scott Antarctic Station of the United States. The pressure vessels I showed you on the previous slide are deployed at a depth between 1.4 and 2.8 kilometers below the level of the ice. This ice is at about 2,800 meters above sea level at the South Pole. We have 86 such holes drilled into the ice. So there are 86 cables going in, and each of those cables have 60 pressure vessels along them. So in total, we have about 5,200 photomultiplier tubes embedded within the ice in a three-dimensional array. And the total volume of IceCube is about 1 kilometer cube. That is 1 kilometer by 1 kilometer by 1 kilometer. It's not exactly 1 kilometer in each dimension, but it has a total volume of about 1 kilometer cube. And so you can see the Eiffel Tower here for a scale comparison. This is much larger. It's one of the largest particle arrays in the world. And this array is able to detect neutrinos. I will explain to you how. But at the heart of it is an effect known as Cherenkov radiation, which is that if you have charged particles and they're traveling through a medium, so a transparent medium, could be glass, ice, anything. And if they're highly energetic, what can happen is they can travel faster than the speed of light in that medium. Nothing can travel faster than the speed of light in vacuum. That's forbidden by the laws of physics. But if you have a medium, the light travels at a slower pace within the medium due to interactions with the atoms and molecules and the electrical structures that make up that medium. And if you have a charged particle that's highly energetic, it can travel faster than light can in that medium. Then you get, you may be aware of the concept of a sonic boom. When you have a fighter plane that crosses the sound barrier, you have this cone within which the signals get amplified and it can break your windows and stuff. The exact same or an analogous physical process, but with electromagnetic fields, happens within the medium, and it leads to a cone emitting light, visible spectrum light. So any charged particle that is highly energetic and is going through a transparent medium will emit visible spectrum light. And this phenomenon was discovered by Ilya Frank and Igor Tamm, two Soviet physicists, both of whom received the Nobel. Sorry, this phenomenon was explained by them, and it was discovered by Cherenkov, another Soviet physicist. All three of them received the Nobel Prize for discovering this, because the Cherenkov emission of charged particles, high energy charged particles, one of the most common ways in which in high energy physics we detect these particles, we measure their properties, etc. So IceCube uses basically the naturally occurring ice at the South Pole as its transparent medium in which the Cherenkov radiation is emitted by charged particles, and we detect those charged particles by using these nanosecond resolution photon counters that I spoke about on the previous slide. So if you were to fly to the South Pole, this is the outline of the IceCube detector that you would see. This is the geographic South Pole and the Amundsen-Scott station. You don't actually see the outline of IceCube because it's buried deep under the ice, but you can see the IceCube counting lab here. This is where the cables from all the 86 strings come in, and we have a processor farm that handles all the data. So the IceCube collaboration, the team of scientists around the world which operate this instrument, consists of about 28, more than 40 institutions spanning 28 countries, the majority of which are in the US and Canada, but there is also a set of European institutions, Japan, South Korea, Australia, and New Zealand involved. The next generation of IceCube will also have India involved with me helping out in it. I will talk about that towards the end of this talk. The reason we want to see the universe in neutrinos, and this is because, with particle physics, based on our knowledge of how these particles interact and how we believe the universe is, we can make estimates of how good photons are, how good charged particles are to give us information about the universe. And the basic idea is that once you go to high energies, you want to see very hot processes happening in the universe, jets of high energy particles happening out there, etc. If you want to look at the photons that come from it, those photons do not travel very far in the universe because there is a ambient distribution of thermal photon known as the cosmic microwave background, which is left over from the Big Bang. And that medium makes the universe opaque to high energy photons. So at an energy corresponding to 1 peta-electron volt or so, which is like one of the highest, it's about 20 times the energy that you achieve at the Large Hadron Collider in Geneva. If you want to see the universe at those high energies, photons can travel only till about the distance to the center of our own galaxy. So, our galaxy is a small island universe in a universe in which there are various other galaxies, many of which are at hundreds to thousands times the distance we have to the center of our own galaxy. And with high energy photons, we can really see only as far as to the center of a galaxy, not more. There is no probability that high energy photons will travel further because they will interact and the universe essentially becomes opaque. And with charged particles, cosmic rays that I mentioned also, they also do not travel too far because they also interact with this background of photons that exist in the universe. But neutrinos, on the other hand, they don't carry electrical charge, so they don't interact with photons. They don't carry color charge, the force that holds nuclei together. So they're effectively, the universe is completely transparent to neutrinos. If I hold out my thumb right now, there are about 60 billion neutrinos going through it per second. These are relic neutrinos left over from the Big Bang. At least we believe it is so. We have not ever actually detected them. Maybe in 40 years, there'll be an experiment that tries to, and it might turn out that they don't exist, which it might be cool. But right now, we believe there are about 60 billion neutrinos going through your thumb every second. And that's because neutrinos are extremely weakly interacting particles. Everything is transparent to neutrinos. The Earth is transparent to neutrinos. The entire universe is transparent to neutrinos. So if something is, if it's transparent, like everything is transparent to it, how do you detect it? That's why we have a 1 kilometer cube detector. So a neutrino, the probability that a neutrino will interact with something is about 1 in 100 million compared to the probability that a photon will interact with something. So to detect photons, you have an instrument the size of your eye, but to problems over the last century that we were convinced that only neutrino astronomy can help us make progress in. And again, it's about the motivations of bringing together large amounts of resources to answer questions, because the IceCube Neutrino Observatory cost about $400 million to build, and it costs around $10 million a year to operate because the South Pole is a very hostile environment and you have to place people there. And to gather all of those resources from around the world, from multiple countries, like I told you, and create such a facility in effectively no man's land. Antarctica is not a country. It is governed by the Antarctic Treaty, which has many countries as signatories in it. And to create such an infrastructure, you have to really need a strong reason. And the reason is this. Over the last 100 years, we have been seeing charged particles coming from outer space. We don't know where they're produced because they're charged, and so their trajectories do not point back to where they were produced. But some of them have energies up to 10 million times the maximum energy we are able to create in a lab on Earth. So the Large Hadron Collider creates particles of up to 7 TeV or 13 TeV in center of mass when you collide. Here you have particles coming in from outer space which have 10 million times the energy of one of those particles. And the question is, how is nature able to accelerate something to energies much larger than we are able to? Because to get particles to accelerate to 7 TeV at the Large Hadron Collider, you need a precise alignment of dipole magnets over a 27-kilometer tunnel. That it is an engineering marvel, but nature seems to be throwing this at us from outer space. And we have known this the evidence is built up over the last 100 years or so. Now, people who study this have some notions of how this came about. a Swiss astronomer called Fritz Zwicky looked at how stars explode, and he calculated the velocity of matter falling from stars exploding and being ejected out from stars exploding. And he looked at the energetics of it, did some accounting, and came to the argument that if supernovae, which are exploding stars, are able to transfer just a few % of their energy into high energy particles, that is sufficient to sustain all the high energy particle flux we see in our galaxy. So this is an energetic argument. You know, if someone builds a really expensive big house, then you can say, oh, this is really big, and only these many people have the required wealth required to be able to build such a house. So then you can kind of guess at who's doing things. Similarly, the amount of energy required to power this cosmic rays means that there are few processes in the universe that are probably capable of supporting it. So exploding stars were for a long time believed to be the reason cosmic rays are accelerated to these high energies, but there's no confirmation. This is conjecture, and to confirm it, you actually need to be able to see a star exploding and see signatures of cosmic rays being accelerated there. But the problem is that the way to see if charged particles are being accelerated there to the highest of energies would be if you saw corresponding photons at the highest of energy, so gamma rays coming from those sources. But such gamma rays can also be produced by other processes. So it's not a conclusive idea even if you see gamma rays from these exploding stars. So it was for almost 20-25 years, there was widespread consensus among physicists that if you see high energy neutrinos coming from any source in the universe, that is a smoking gun signature for particles being accelerated to very high energies in those sources. So this is why people decided that neutrino astronomy is an important thing for us to do. So the array I showed you, IceCube, if you were to read out the pulse waveforms of each of the 5,200 PMTs in the ice continuously, it would produce petabytes of data that we wouldn't be able to handle because we also don't have excellent networking infrastructure all the way to the South Pole. So we use a system of what's called triggers. You kind of, if one of those pressure vessels, the PMT sees a pulse, it'll ask the nearby pressure vessel, did you also see a pulse? And if it realizes that, you know, in some nearby, like 5 within a few microseconds have seen pulses, then it alerts the station at the surface that there is a trigger condition met. Then the station polls the whole detector, it takes all the data and saves it onto file. And this is what is called triggering. It's a standard process in all high energy physics experiments. If you were to look at all the triggered events that IceCube sees, and I will show you a nice video of this later, you see 2 types of events. One is called a track. And so this is a visualization of the array. The colors here correspond to whether the photons were detected early within the trigger window or late within the trigger window. A trigger window is a few microseconds long. The PMTs are able to sorry. I see. Yeah, do you have any questions you can ask at this point?
This is the time to take questions. We will fix this.
Sure. Yes. With? So I will explain. So it's not actually the neutrinos themselves we detect because oh, wow.
And I ended up dropping it.
I hope it has survived. Usually PMTs don't survive drops like this. I'm sorry about that. Destroying equipment on live stream is a... Yeah, thank you. So I will be explaining, answering your question in due time. So You read out different trigger windows of IceCube and you look at how, the detections of photons among this array of 5,200 detectors we have in the ice are, and you can visualize it this way. Oh, okay. Sorry. Why did that stop? I don't remember stopping it.
You took out the cable, right?
I see. So Zoom stopped the screen share.
Yeah. So restart your, reshare your presentation.
Is it better now?
Yeah. And hide it.
Yeah.
This is okay.
Thanks.
Green button.
Yeah.
No, we're
Oh.
still up.
Sorry, everyone, for all the interruptions, but great. So the colors here stand for when the photons were detected. Red means it was early within the 5 microsecond trigger window. Blue means it was late within the 5 microsecond trigger window. The size corresponds to total how much charge was deposited. So if a large number of photons were seen by a PMT, you see big blobs like this, and smaller blobs correspond to less amount of charge. And here, from the clear pattern of hits, even by eye, you can tell that this is like, there is a line, right? It's distributed along a line. And such distributions we call a track. This is a topology. We use the term topology to describe the shape of how hits are distributed within the.
What is CC?
Yeah, I will explain. The CC stands for charge current interaction. And basically a neutrino, because it interacts only weakly and not using any of the other four fundamental, neutrinos are mass, so they are also interacting gravitationally, but they do not take part in electromagnetic interactions, which is the vast majority of physical interactions we are familiar in day-to-day physics, and they do not take part in the interactions that hold the nucleus of an atom together, which are called strong interactions. And neutrino only takes part in weak and gravitational interactions. And weak forces are carried by two particles. One is called the Z boson, the other is called the W boson. Depending upon which particle mediates the interaction of a neutrino with a nucleus, you get different things coming out of that interaction. And that is what leads to these different types of topologies. So this pattern of hits is clearly a line. And we believe, and we have very compelling reasons to believe this, that this is caused by a muon going through the detector. This is the heavier cousin of the electron with about 300 times the mass, but it is not a long-lived particle. After a few microseconds, the muon will decay into electrons and muon neutrinos and electron neutrinos. But while it lasts, it is a charged particle. It has the same charge as an electron, but 300 times the mass. It will at high energies, it can traverse the detector and leave a pattern of hits like this. So I told you there are three types of electrons depending upon which three types of neutrinos depending upon which lepton is their partner. And if it is a muon neutrino that interacts with a W boson mediating it, you get this signature. Whereas all other interactions of neutrinos, on the other hand, do not produce a massive muon which can go for a straight, but instead they produce either electrons or lightweight hadrons, which produce a shower of particles, which then becomes a blob like this. So you can already guess from eye that if you see this, you can tell the direction of the incoming particle to some amount of precision. And what IceCube can do today is about 0.3 degrees or so. So 30% of 1 degree. You can reconstruct the direction of the incoming neutrino, which then interacted to give you this muon to about 0.3 degree precision if you have a pattern of hits like this. Whereas if you have a pattern of hits like this, you really need the accurate timing information, etc., to get even a rough idea of which direction it came from. And currently, the best we can do is something like 7 degrees or so. So, it's like a blob. You get a rough idea of which direction in the sky it came from, but you can't really point if you see these events. And something like 1 in 5 events are like this, and 1 in the remaining 4 out of 5 events are like this. But the advantage of these events is that even if the neutrino interacts far outside the ice of IceCube, as long as the secondary muon goes through IceCube, you see, you end up detecting the interaction in some way. So even though IceCube is a 1 kilometer cube detector, if you calculate the effective volume of the detector for these kind of events, it behaves like a 20, 30 kilometer cube detector. It's much larger. Whereas these events, the track, what is produced after the interaction, all the energy is dumped within a few hundred meters. So as a result, it is only the instrumented volume of the detector itself. The effective volume is effectively just the instrumented volume of the detector. But the advantage, on the other hand, is that because all the energy in the interaction gets dumped within a small region, all of which corresponds to the instrumented region of the ice, we can do calorimetry. You can reconstruct the energy of the primary neutrino that came in with a few tens of percentage probability. Sorry, percentage uncertainty. So with events like this, IceCube is a calorimeter. It measures the energy of the neutrinos. With events like this, IceCube can only put a lower limit on the energy of the neutrino because the interaction happened outside the detector. So there was a lot of energy deposited here. You don't know where. It could have been a very high energy muon produced here or a lower energy muon produced here, and you don't know this. You have a probabilistic information about all of that. So these are the two kinds of events we see in IceCube. We also see some more exotic stuff. Just to elaborate for those of you who have some foundations in particle physics, the tracks are produced by a charge current interaction of a muon neutrino, which then kicks out a lepton, which is the muon in this case, and all other interaction, charge current interactions of the other two types of neutrinos, as well as neutral current interactions where, you know, the neutrino is just deflected a little bit, but in the process destroys a hadron within the ice, and that causes a shower. They all look like these called cascades. And if you stand at the South Pole in front of ice, above IceCube, so here, you look at the distribution of track-like events you see mainly these two types of events. So you have neutrinos which are produced because these charged particles that I told you about interact with the upper atmosphere, and in the shower of particles there are neutrinos produced. And those neutrinos, like I said, the Earth is transparent to them, so they can traverse the entire Earth and they approach IceCube from all directions. So there are neutrinos in the downgoing direction, neutrinos in the upgoing direction. It may seem counterintuitive because the South Pole, so it's a bit, you know, this picture is a little upside down. And those we see about 80,000 of them per year. On the other hand, these muons which actually leave this track after a neutrino is introduced, these muons are also produced directly in the upper atmosphere in the interactions of the charged particles with the upper atmosphere. And we see about 70 billion of those per year. That's about 2,500 of them every second. Okay. And the neutrinos we see, on the other hand, are 1 every 7 minutes or so. A track corresponding to a neutrino. But the advantage is that if it is in the upgoing direction, so if you're standing at the South Pole and you see the track is going up, it has to be a neutrino because it cannot be a muon produced directly in the upper atmosphere because muon cannot travel across the entire Earth. It's only a neutrino that was produced here which crossed the Earth and interacted somewhere here to produce a muon, which could have been the reason for an upgoing track. Whereas in the downgoing direction, it's very hard to tell muons directly produced in the upper atmosphere and neutrinos interacting near the ice apart. We still have some techniques which I'll talk to you about. But so if you were to look at the cosinus of the angle and plot the distribution of these tracks, you see that in the downgoing direction, which corresponds to the southern sky, you have a 6 orders of magnitude larger background of muons compared to the neutrinos, which, because the Earth is more or less transparent, is uniform in all directions. Like the atmospheric neutrinos are more or less isotropic in their arrival directions at IceCube, but atmospheric muons are predominantly downward going. So here is a video which illustrates this point nicely. This is 10 milliseconds of IceCube data, so 1/100th of a second. But you can already see that there are something like 250 tracks here, right? So I will just play it again maybe to give you an appreciation. So this is 1/100th of a second of IceCube data visualized. And you see these tracks, those are what we infer from the pattern of hits within each trigger window. And you see that the vast majority of those tracks are downgoing. In fact, to see an upgoing track, you will need to wait for, you'll need to make a video of 10 seconds of, 10 minutes of IceCube data. So in 2013, IceCube announced to the world that we had discovered astrophysical neutrinos, and this was on the cover of the Science journal, one of the most prestigious journals in physics, and it was later on picked by Science as one of the most important discoveries of the decade. And the analysis behind that is actually remarkably simple. The idea is that we want to get rid of these muons which are produced in the upper atmosphere, which are produced at the level of 2,500, which we detect at the level of 2,500 every second. And we want to look at only the neutrino-induced tracks. And to do that, we looked at only the highest energy events, and two, we used the outermost layer of the detector as a veto. So if you have a muon that was produced in the upper atmosphere and it's coming into the detector, it will also leave hits within the outermost layer of your detector. If on the other hand, we insist that the trigger window should not have any photons in the outermost layer of the detector being detected within the trigger window, then you are selecting for events where the neutrino traveled into the detector, interacted within the detector, and produced a muon track. So we looked for those kind of events. So this is the logic behind it. You look at the total amount of charge deposited within the detector, take each PMT, take the area under the curve of all the pulses, you add them up, and then within the trigger window, you look at just the triggers which had the maximum amount of charge. So charge associated with event at the largest end of this, and charge in the veto region on the other hand at the lowest end of this. So in the outermost layer of the detector, you look at the minimum amount of charge possible. You require the minimum amount of charge possible, whereas in the bulk of the detector, you require the maximum amount of charge possible. So you're finding neutrinos in a haystack. It's a needle in a haystack problem. And this was the technique we used to isolate these events. And in particle physics and in astroparticle physics, the moment we gather data from a real detector, we always have a set of physicists who are producing what are called Monte Carlo events. These are simulations of the detector and our understanding of the physical hypothesis, which allows it to produce fake data sets that look very much like the real data set. And it is by comparing the fake data sets with a deep understanding of what physics we put into the fake data set and the real data that we come to physical conclusions. So what this plot shows us is the total number of events detected at different energies. And you see that at the highest of energies, there is these data points lie here, and the total Monte Carlo, that is the expected background, drops off here. So there is a clear excess over what we are able to explain. And that excess, which has not been accounted for in our Monte Carlo process, could be explained only by the fact that neutrinos are directly coming in from outer space. So earlier I told you about neutrinos produced in the upper atmosphere because cosmic rays are interacting there. Then I told you about muons directly produced in the upper atmosphere. Now there are neutrinos produced out in space, which are arriving at Earth. And these events, the excess, the fact that there are more events here than the Monte Carlo background can explain, can be explained only by invoking the hypothesis that we have seen astrophysical neutrinos. We have, there's a lot more detail of logic and tests, and the multiple papers have gone into building the confidence to saying that we have actually detected astrophysical neutrinos, but I'm giving you a oversimplified story. So great, we can use neutrinos to do astronomy. So we take these events which we believe are coming from outer space, we plot the direction in the sky. So this is called a Mollweed projection. Those of you who are familiar with maps would have heard of map projection. There's like a Mercator projection which allows you to visualize the surface of the Earth on a flat surface. Similarly, this is a similar projection that astronomers use to visualize the 4-pi sky on a flat surface. And this is, for example, the plane of our galaxy. And you see the color dots correspond to hotspots of these high energy neutrino events. Now, some of these spots look really hot, so you may think it's a source, but if you pay attention to the statistics of it, it is likely that it was a random coincidence. You just take a bunch of sources that are randomly distributed across the sky. You do occasionally get those hotspots. It's only by saying that the hotspot we see is too unlikely to have come from random processes can we claim that we have actually seen a source. So there is no source in this image. It's just showing you the sky distribution of these neutrino events. The other thing is that you see that many of them are big blobs. That's because the majority of events here were not tracks but cascades, because I told you 4 out of 5 interactions produce cascades, especially if you're using the outermost layer of your detector as a veto. All the tracks that were produced from interactions outside the instrumented region of IceCube, which I told you, for tracks we have effectively a much larger effective volume than the instrumented volume of IceCube. That because we are using the veto, we kill that effect, and we are only using the instrumented region of the detector as our detector. So we basically see majority of these events are cascades, and they don't point back. They're within 7 or 8 degrees. So doing astronomy with this is quite difficult. But we got the clever idea starting in 2016 that it is important to inform the world about these events as soon as we see them. Okay. Now there are reasons for the optical telescopes. If you want to see something, you have to point them in that direction. IceCube is just a block of ice. You can't point it. It's a 4 pi detector, meaning the entire sky can be imaged in neutrinos at all times simultaneously by IceCube, because it's just a volumetric array, and the Earth is IceCube is like the eye of Sauron. It sees through everything. But you cannot say that for gamma ray telescopes, for optical telescopes, etc., which need to be pointed. And if you don't happen to be pointing in the correct direction with these instruments, you miss out on interesting things happening in the universe. So starting in 2016, we set up a system to infer information from these events the moment the detector is triggered, and alert as wide a community as possible of astronomers as soon as possible. And I was one of the people involved in the effort in setting up this system. This system, when we first started out to infer the direction from one of these triggered events, it took us 40 hours of computation. But then we figured out how to use mathematical tools called splines and a whole bunch of things to make all the computation faster. And by 2017, we were quite often sending out alerts within 17 seconds of the detector being triggered. So you have the detector being triggered within 17 seconds, and Iridium satellite in geostationary orbit around Earth gets a signal from IceCube. The satellite relays it to a control center in the northern hemisphere at the Wisconsin IceCube Particle Astrophysics Center. And then that information is sent out as things called astronomers' telegrams, gamma ray coordination networks. There's a whole bunch of networks of astronomers of different energies who coordinate real-time information with each other. So we had this idea that this would be useful. We set up this system and we started sending out alerts. And I was on the real-time oversight committee at that time, which at each time an alert happens, and this sometimes happens like at 3 in the morning, and you have to wake up and run your reconstructions and monitor the data. So we sent out 10 alerts. We sent out 9 alerts actually. And even though we put in a lot of work on each alert, being very careful, nothing happened. The alerts just went out there and people just ignored it. Or people did things, but we didn't see anything interesting coming out of the community. But in 2017, September 22nd, I remember this very well, because it was at 7 p.m. in Copenhagen time where I was, and I was actually very drunk, and I got this message. So I went and started the cross checks. The alert went out, and within 3 days, we had a series of publications, fast-tracked publications called astronomers' telegrams from other observatories around the world, telling us that in the direction of the event we sent out an alert for, they also see interesting activity that is happening at that time. And I'll tell you what that activity was. But this event, the fact that we sent out an alert and multiple people responded and almost immediately, and then they published what they found, that came to be known as the birth of real-time multi-messenger astronomy. So I told you on the first slide, you have different types of messengers and a 400-year history of using light, then light in different wavelengths, then cosmic rays, then gravitational and neutrinos. The fact that the last 2 messengers, gravitational waves and neutrinos, happening, the astronomy with those messengers happening in the era of the internet, means that now all of this information is also interconnected and networked, and all of these observatories are now talking to each other in real time. So This is a new development called the birth of real-time multi-messenger astronomy. My microphone seems to have changed. Am I still audible? Yes, I'm sure I'm audible in the room, but people over Zoom.
Yeah, go ahead.
Yeah. So, what has happened is that we sent out this alert within 2 days. There is this imaging atmospheric Cherenkov telescope, which is a telescope that uses the upper atmosphere as a medium to detect very high energy gamma rays. They responded with an astronomer's telegram pointing out that they saw a source they were tracking in that exact same direction to be in a state much higher. Like they had been tracking how many gamma rays that source is producing over time. And during this period, that source was producing about 10 times as many gamma rays as it was in other periods. And these sources are known to, like, the total amount of light or gamma rays produced by them at different energies all vary significantly. So if you plot them against time, you see a curve that's, fluctuating a lot. So they are highly time variable sources, and multiple telescopes informed us that in the direction of the event we sent out, they saw a flaring source. So I told you that IceCube can reconstruct sources to a precision of about 0.3 degree or so. So with 90% probability confidence, this is the area on the sky. So these coordinates correspond to directions in the sky. Right ascension is direction along one axis, declination is the direction along another axis within a celestial coordinate system. And this region of the sky you're looking at is under the arm of the Hunter constellation. And this object, the 90% probability confidence contour of IceCube is shown by this dashed curve. Gamma ray telescopes have better angular resolution than them. They can go down to 0.1 degrees, which is why you see that their contour is even smaller than that of IceCube. And there is a source there, something called a blazar. People believe these are black holes that exist at the center of a galaxy, and there is a jet coming out of that black hole, and that black hole is pointing, that jet is pointing towards us. If that jet is pointing directly towards our line of sight, that's called a blazar. If that jet is pointing perpendicular to our line of sight, people call them radio galaxies, Seyfert galaxies, etc. Fanneroff-Rayleigh galaxy, whatever. There's a lot of terminology. Astronomy is a bit like biology. It's very taxonomical. They keep classifying things. So we saw that this source, now people did the statistics of could this have happened randomly? I mean, the IceCube neutrino, we are not 100% sure it came from here. It could be within this region. But we worked out the statistics of that, and we figured out it had about a low probability of about 1 in 1,000 of happening by random coincidence. So it's not like particle physicists, when they claim they have discovered something, they like to say phi sigma. And that is because they want to be sure the level of 1 in 10 million or so, that this did not happen by random coincidence. But in astronomy, we don't have the luxury of doing our own experiments. We have to kind of work with what nature gives us. So 1 in 1,000 gets some people excited. But more importantly, motivated by this, we went back and looked in that direction at the data. And now when you have a specific reason to look in one direction in the sky, a lot of the statistical noise you're able to eliminate. And in the archival data, we found another about 1 in 3,000 probability excess of events from the same direction. So this source, the TXS 0506 plus 056, which is a blazar. This is an artist's impression. So this is the jet that is pointing towards the Earth. And you can see how neutrinos are produced in that jet in terms of all the intermediate particle physics processes, as has been illustrated here, is now known as the first multi-messenger source, because it has been seen not only using photons, but also using a massive particle, neutrino. No other source has been. The sun has been seen in photons and also neutrinos, but the neutrinos from the sun, we don't really reconstruct their direction, and you don't image the sun using neutrinos anymore. And so this is definitely the first extragalactic, in the sense it's far outside our own galaxy. Now, one of the advantages of real-time multi-messenger astronomy is, of course, people get excited, and then excitement creates its own its own momentum. But the other thing is that when you have information from another messenger telling you some region in the sky is important, you accelerate the gathering of relevant data, because it allows you to target on things that you are more interested in for your hypotheses. And so in the subsequent 4 months after our alert was sent out, this source became the target of intense scrutiny among a large community of astronomers across all wavelengths around the world. And optical astronomers pointed their instruments at it, and they were able to measure what is called its redshift, which tells you how fast this thing is moving away from us because of the expansion of the universe. Then if you have a cosmological model, you can use that to calculate the distance. And it turns out this is about 4 billion light years away from us. So the biggest puzzle at that point was, why is the first source we are seeing in neutrinos so far away? I mean, there are so many more blazars that are much closer to us, within a few, within just 1 billion light years around us, a few 100 million light years around us, there are way more. But we have not seen any of them producing neutrinos. But we are starting to now see also other sources, and these puzzles are slowly starting to be answered. But this continues to be a puzzle that everyone is surprised that the first source of TeV neutrinos we saw turned out to be so far away in the universe, not a very nearby galaxy. So those of you who are familiar with astronomy might have heard of something called a spectral energy distribution, which is you look at a source in different wavelengths and you plot how bright it is in different wavelengths. You compile all of that information into one plot. So this energy corresponds to the wavelength if it was multi-messenger astronomy, multi-wavelength astronomy. But for the first time, we have what is analogous to a spectral energy distribution, but also including multiple messengers. So you just have not just photons, but you see here you have neutrino information on a spectral energy distribution. So this is what happens when you start seeing the sky in new particles. Subsequently, we have looked at samples of through-going tracks that go through the detector, and you ask, is there a cluster, an excess of many events in one direction of the sky that is incompatible with the background? And we have actually seen one more source at about 1 in 3,000, 1 in 4,000 probability. So it's not at the very conclusive level where particle physicists will say we are definitely sure a source has been seen, but there is strong motivation to look in this direction and study this source, which is there's a nearby. It is also a blazar. It's a black hole with a jet pointing towards us, but we believe that the jet is obscured by dust, because based on how many neutrinos are coming from it, you can predict how many gamma rays should be coming from it. You don't see that many gamma rays. So then the idea is that the gamma rays are being absorbed somewhere in between. So this is a feature of the field. Complexity gets added on layer by layer to explain data. It is not, you always start with a spherical chicken in a vacuum. You have like a one zone model where it's all uniform, and then you try to predict the number of events. You don't get those events, so then you match them, and then to get them to match, you add layers of complexity in between. Astronomy is being done in a very reductionist way, even though the systems under study may not be amenable to reductionism. But the basic idea is that you look in the direction of that source and you see a clear excess of events over the background expectation. So again, the background expectation is from Monte Carlo datasets that I told you about. And this excess can only be explained by the fact that the source is itself emitting neutrinos towards it. So this NGC 1068 is like the second source we have seen in high energy neutrinos. So now, most recently, 2 years ago, we published a paper in Science demonstrating that, I think my pointer is dead, but it's fine. Demonstrating that we saw our galaxy in neutrinos. So we have been seeing our galaxy. This is the Milky Way. The Milky Way is more visible from the southern hemisphere of the Earth. So if you were to go to Malargüe or some part in South America or Chile, where the European Southern Observatory is, and you look up with an optical telescope, you will see this thing across the sky known as the Milky Way. Now, if you point gamma ray telescopes in the same direction, you see something like this. And the Milky Way has been seen in practically every messenger that we use to image the sky. The gamma ray information can be theoretically interpreted to predict how many of those photons that we see in gamma rays came from high energy charged particle processes. And then based on our understanding of how high energy charged particles interact, we can predict how many neutrinos should be produced in those processes. Based on that, we have this template which predicts how many neutrinos should be produced by the galaxy. And we used a convolutional neural network to interpret IceCube data and extract the number of events. And you see something very similar. So this is the predicted neutrino map of the galaxy, and you see exactly that. And this is again at a statistical significance of 1 in 100,000 or so. So what people call 4 sigma. It's still not the 5 sigma that particle physicists want, but it's starting to become very compelling. So humanity has opened its baby neutrino eye and captured its first blurry glimpse of the cosmos, and you clearly see the galaxy there. The galaxy, is a real thing. Cosmologists don't really accept that, but I'm trying to convince them of it. The other thing is that the thing you need to understand about neutrino astronomy is that unlike visible spectrum astronomy, where you can, or radio astronomy, where you can measure angular separation between objects, etc., the precision of by 10,000th of a degree or so, a few milliarc seconds. With neutrinos, you cannot really image the sky to that precision. The best resolution you can ever get with the best detector will be like maybe 0.1 degree. So it's always going to be a blurry picture of the sky. But the advantage is that neutrinos allow you to see into the densest parts of the universe from which light cannot escape. And they allow you to image the entire universe at various energies, whereas light is opaque. I mean, the universe is opaque to light at high energies. So neutrinos, it's a new window to the universe, giving you a different picture of the high energy universe. The other major event over the last 10 years in what is called real-time multi-messenger astronomy was the detection of gravitational waves by LIGO-Virgo collaboration, 2 laser interferometers, 3 now, 2 in the US, Hanford and Livingston, and 1 in Italy somewhere. And they've seen these black holes colliding, and the data they have in their interferometers suggests that black holes that are rotating around in each other and then merging to become one black hole has been imaged. Now they are able to figure out where in the sky those happen, but not with the precision that you can with IceCube. So then the question is, could the same event have produced also neutrinos and gravitational waves? And we looked for that, and we have so far not found any events that produce both neutrinos and gravitational waves. A major publicized event in about 2016 was when they found gamma rays that came from an event which also produced gravitational waves, which then they concluded was because there were neutron stars colliding. In that event, we did not see neutrinos. We have what is called an upper limit on the neutrinos. And now theorists have done a bunch of sophisticated calculations, and they're saying that in that event where 2 neutron stars merged, the jet that was produced was about 17 degrees off axis from our line of sight. If that jet was aligned to our line of sight, maybe we would have seen 1 or 2 neutrinos in IceCube. But this is like saying if my grandmother had wheels, she'd have been a motorcycle. So it's a prediction. That if we see an event like this happening and the jet happens to be aligned to our line of sight, then IceCube will also see some neutrinos. Then you'll have the same event being imaged in high energy photons, gravitational waves, and neutrinos. It will happen in the near future with some probability. So the other advantage that IceCube has is that because we see so many neutrino interactions, we can use them to study the properties of neutrinos themselves. So instead of looking at it as an astronomical observatory, you can think of it as a particle physics detector, and you can do similar kinds of studies with what they are doing at the Large Hadron Collider in Geneva. So, for example, I'll just give you one example. This is during the birth of the standard model of particle physics, when these few particles were being discovered and being organized the way people understand them today as the standard model of particle physics. Sheldon Glashow, who went on to win a Nobel Prize, one of the fathers of the standard model of particle physics, he predicted by looking at the number of particles they had already seen that there is a very unique interaction that a neutrino should take part in. And this later on came to be called the Glashow resonance. And at the time he wrote this paper, he was at the Institute of Theoretical Physics in Copenhagen, Denmark, which was the home of Niels Bohr, which had been turned into an institute. And subsequent to the death of Niels Bohr, this got renamed to the Niels Bohr Institute, which is where I was working. And while I was a postdoc at the Niels Bohr Institute in Copenhagen, we saw this event. Now, the interesting thing was, at the time Glashow made this prediction, he did not know the mass of one of these particles called the W boson. So you kind of make an assumption about that mass, and you predict how much energy the neutrino needs to have to see this phenomenon. And that prediction already at that time was beyond was at an energy beyond that which is achievable at any collider on Earth. So, but eventually they measured the mass of the W boson. It turns out you need 1,000 times the energy that you can get at the LHC within a single neutrino to be able to see this phenomenon, a resonant production of the W boson. But in 2017, while I was the postdoc at the Niels Bohr Institute, we saw such an event with an IceCube. And this is possible only because we have nature giving us these high energy neutrinos. We will never be able to accelerate particles to these. Okay, I will not say we'll never be able to. Maybe 100 years from now, they'll have awesome technologies that I cannot think of right now. But right now, if you wanted a particle at this energy and you wanted to create it on your own, you would need a tunnel 100 times the size of the LHC. And that would cost $1 trillion, which no one's going to give you. So with the current energy of the Large Hadron Collider, there is a certain energy that you can reach for neutrino particles. If you want to study particles at much higher energy than that, the universe has to give them to you. You cannot create them yourself. This is why astroparticle physics is relevant. Has a competitive edge over particle physics. So we can also do things like measure the density of the Earth by looking at neutrinos, because even though I said the Earth is opaque to neutrinos, this is a statistical statement. A few number of neutrinos do get absorbed at certain energies within the Earth. So you can look at the angular distribution of how arriving neutrinos are distributed, and then you can use that to map out the density of the Earth. Or conversely, you can assume the density of the Earth using seismic data. Then you can measure properties of neutrinos that way. So we have done studies like this. This is something that IceCube is good at doing. Another thing is that the 2017 Nobel Prize in physics was awarded for the discovery that a neutrino that starts out as, let's say, an electron neutrino will later on may turn into a muon neutrino. This is called neutrino oscillations. And it was very surprising for people because the standard model of particle physics did not predict it. It actually means that neutrinos have some mass. They are not massless like photons. The mass has not been measured. Now, IceCube is able to measure the parameters using which neutrinos oscillate by looking at the distribution of how many events as a function of distance. So, you have the Earth. So the upper atmosphere is about 10 kilometers above the surface of the Earth, and you stand here, and then depending upon the direction you see the event from, you have the total distance the neutrino has traveled, because it is given by geometry of the Earth. And then you can reconstruct the energy and the probability that a muon neutrino will turn into an electron neutrino and vice versa, etc. These can be measured by comparing against Monte Carlo again. So this is the actual data we see. This is what we should have seen if neutrinos were not oscillating. Because the data we see falls over this line and not this line, we are able to measure parameters of how neutrinos oscillate. So this is with, we are competitive with experiments that create their own neutrino beams on Earth. So we are using neutrinos that nature gives us to study the properties of neutrinos, and we are able to do that as precisely as experiments which have their own neutrino beams. So in summary, in the past decade, we have discovered that there are neutrinos coming in from outer space on Earth, and we have learned to detect them, image the universe using them. We have developed a new astronomy, opened a new window to the universe using these particles. And neutrino astronomy today is at a stage where gamma ray astronomy was in like 1970s. In 1970s, they had realized the same thing about high energy photons, that there are high energy photons coming in from outer space. And they had discovered a few sources. They had discovered something called the Crab Nebula, maybe seen the galaxy as a whole. And same way, neutrino astronomy is currently in that stage. We know there are neutrinos coming in. We know one or two sources. We have not really resolved the whole sky in neutrinos. And that, to do that, we will need to build a detector that is 10 times larger. So the existing IceCube is what you see in red here. We have a plan to build a detector that spans 10 times the volume of IceCube, because 10 times the volume of IceCube means, you know, about 6 to 10 times as many events, because it's the cross-sectional area that determines how many events you have. And so more events means you can image the sky faster. And the plan is to do this not at 10 times the cost. And the way we do that is you just put these optical modules, the pressure vessels I showed you on slide 1, further apart. Yes.
Ask this one thing. Can we build something like IceCube using the existing permafrost in like the Arctic region of like Siberia or whatever?
Sure, but the problem is that Siberia, they have something called Lake Baikal, where they have a neutrino detector. The Russians actually operate it. That detector is only currently 1/10 the size of IceCube. So if IceCube sees 10 astrophysical neutrinos per year, that may be seeing 1 astrophysical neutrino a year. And they have not actually claimed it, but Russians do everything in a little isolated way. But there is a Lake Baikal in Siberia that it's not in the permafrost. That lake melts during the summer. So it's during the summer it is a water Cherenkov detector, and during the winter it's an ice Cherenkov detector. And ice and water have different optical properties. So there are other detectors. In fact, I plan to mention that. There was a proposal to use the ice in Greenland to build something like IceCube. I did some studies for it. It's because of these regions, there are also the political issues. Like Greenland is part of the Danish realm, but they are autonomous and they don't want Westerners coming and meddling in their areas, etc. So, but you do have naturally occurring ice that is kilometers deep in many parts of the world, and as long as it's reasonably transparent, you can use it to build a neutrino detector. So it's possible anywhere. You can also use the oceans. So there is a detector called Antarctica that is operating now, which is being expanded into something called the kilometre cube net by European Union. And then there are China plans to build something called Trident, which is 10 times bigger at the onset. And they've already started deploying the strings also. So because we have started neutrino astronomy over these 10 years, now there is wide interest in building as many neutrino telescopes as possible around the world. And there are various efforts. So there are multiple ocean-based neutrino detectors under construction, and there is IceCube at the South Pole, which we plan to expand. Yes.
What other kind of neutrino detectors where there's a big room underground with the detectors, like a lot of detectors there inside?
Yeah.
Is that better or regardless of size? As in, suppose it was the same size as this IceCube, would it be better or worse if I'm detecting neutrinos?
So it's a question of quality versus quantity in a manner of speaking, but it's also about economics. What those detectors do is they are able to, when I showed you this interaction in the beginning, I will go back to those slides. Yeah, these sort of interactions look like this only because IceCube is detected instrumented very sparsely. Along each string, there is a 17-meter distance between the pressure vessels, and between the strings, there is 70-meter distance. Now, if you actually reduce those distances, kept them just 3 meters apart or made a denser array, you wouldn't see something like this. You would see a lot of substructure to these. And those substructure would allow you to do a lot of particle physics more accurately. This is why you have smaller neutrino detectors that are more densely instrumented, because you get to see minor, like fine-grained details of the interactions more precisely. And that allows you to study various properties of the neutrinos, look for new particles that may be produced in neutrino interactions, a whole bunch of things that IceCube cannot do because we are a dirty, non-fine-grained detector that's too sparsely instrumented. Okay, so it's about what you want to do and what you expect to do, and also the economics of it. So, for example, if you had to build IceCube with the density of one of these detectors you're talking about, like Snow Lab, you're probably mentioning something like Snow Plus or Hyper Kamiokande or Super Kamiokande. Okay. If you wanted to build IceCube with the density of instrumentation of those detectors, it would again cost like billions of dollars. Nobody's going to give it to that, give us that. So yes, doing experimental physics involves having to understand things like money, which is very complicated. So, so our next plan of the IceCube collaboration is to build a 10 times bigger detector at comparably the same cost as IceCube. And how we are going to do it is we're going to just place all the strings further apart along a string. We'll place the detectors further apart, and we'll just span a bigger volume. And so this means that the further apart the detectors are placed, you can see only higher energy neutrinos, because maybe it'll turn out a low energy neutrino will interact, but it will not go to the next DOM and trigger that also and tell, generate a trigger. So this is how things work. The further apart the detectors are, the lowest energy you can detect moves higher. But the further apart the detectors are, you can build a cheap detector array, much larger than the existing detector array, which means that you get to see more high energy events. So those are the trade-offs that you have to consider. And the basic idea behind this is that it will be able to resolve a source in the sky that for IceCube might take 30 years. It will be able to do in 5 or 6 years. So that is why we want a 10 times bigger detector. It will have new technologies. So IceCube currently uses only these photomultiplier tube based pressure vessels, but people have been experimenting with using the same set, the process, the interaction that produces the light which our photomultiplier tubes detect. Those interactions also produce radio waves. So if you were to embed radio detectors in the ice, you should be able to detect using radio also some neutrinos, and we have some technologies related to that which we are exploring. In the IceCube Gen 2 collaboration, you will be glad to see that India is also blue in this map. The TIFR group is involved in that, and this new detector, my postdoc is working on Monte Carlo simulations so the detector itself is below the ice at between 1.4 kilometers and 2.8 kilometers. But on the surface of the ice, we put another set of detectors which serve as a secondary V2 to measure the cosmic rays that are landing on top of the cosmic ray secondary particles. Then the digital optical modules itself, this is the one that is there in the current IceCube detector, and you see there is a single PMT pointing downwards. But now we are experimenting with many other types of optical module designs. This, for example, has 24 individual narrow PMTs pointing in different directions. What this allows is each module, when it sees a photon, it will, with this, you can not just say that a photon has been seen, but also which direction the photon came in from, with in a pixelated way. Here, for example, you have 2 photons, but the advantage is that because the pressure vessel is narrow, you need to drill only a narrower hole, and that makes the deployment process cheaper. So there are all sorts of economic and engineering considerations to be considered. TIFR is now starting to get involved in the construction of this. So we have my student Ashish Narayan and a student from the Institute of Physics in Bhubaneswar, Krishnamurthy, who is currently about 2 weeks back, or maybe a month back, they were in Japan. They were assembling and programming these digital optical modules. And this winter, for the upgrade, they are going to be deployed. Well, this is not the 10 times bigger detector, but to be able to deploy the 10 times bigger detector, we need to kind of start deploying one string at the center of a few strings at the center of the detector and so on. There is a elaborate expansion plan. But Indian students working with me and another faculty member in IOP Bhubaneswar are involved in this effort. They're involved in producing Monte Carlo simulations. They're involved in writing firmware for these devices, etc. So I think with that, I will stop the talk. Sorry.
Okay,
Yeah.
so thank you, Ramesh, for a fantastic talk. What we'll do is we'll take a tea break, and then we'll come back, and then Ramesh will be at your mercy to answer everything about what we discussed.
Sure.
So let's take a tea break.